For this lab, we were given a video of a spring mass system moving in two directions and asked to use Newton's second law and the energy principle to construct a model of the motion. Newton's second law, which has been used in the previous labs, deals with the equations to update the velocity and time and position. In this case, the total net force is made up of the force of the spring on the mass and the force of the weight due to Earth's gravity. The spring force is equal to the spring constant K sub s times the absolute value of the stretched length minus the relaxed length, which is s. And in order to find Ks and L naught with the information from tracker, these following equations were used. The oscillation period t was found by taking the third cycle and dividing the time by 3. The Ks value was then used to find the L naught value in the next equation. The energy principle equations deal with kinetic and potential energy and the conservation of these values. The principle states that within the system chosen, which in this case was the Earth, the mass, and the spring, the total change in energy should be 0. This means that the work done by the surroundings should be 0, so the addition of the kinetic and potential energies from the Earth and object and the spring should also be 0. Those equations look like this. This is the kinetic energy equation. This is the equation for the potential energy due to gravity, which in this case was chosen in this form because the system is close to the Earth. And this is the spring potential energy equation. Because the system chosen has no surroundings, the total change in energy is 0 because there's nothing acting on the system. This is the video given by Tracker, and these points that are shown are the point mass data points that I chose. You can see the 2D motion in both the x and y direction, the choice of coordinate system with the motion centered on the negative y-axis, the calibration stick used as 0.70 meters from the fixed point to the mass when the spring was relaxed at the beginning of the video. Notice also that the motion here is a sine wave. In order to create a functional, useful, and accurate computational model of the motion, many of the equations shown previously had to be input into the code along with other relevant data. The spring constant found with the equation mentioned before was found to be 5.86 newtons per meter. L naught was found as 0.074 meters. The mass was given as 0.402 kilograms. These equations correspond to the code's way of finding the L, which is the position at that time, the L hat, which is the direction that the spring is changing the length in, S is the magnitude of L minus L naught, which is the relaxed length, kinetic energy equation, potential energy equation due to gravity, the spring equation for potential energy, the gravity, the spring force, and the net force, which is the addition of these two, the ball final velocity using Newton's second law, the ball position equation using Newton's second law, the kinetic energy equation, and those are all the equations used that were mentioned before. When run, the code looks like this. From this graph, we can see that the energy principle was satisfied because the yellow line indicating this value is shown at 0, meaning that there was no change in the total energy of the system. For the oscillation period, whether x or y is used does give a different value. T was used in my equations because it is constant as opposed to the value obtained from the x positions, which is not constant. This discrepancy is why the model shown here is not completely accurate.